Thank you. Thank you very much for your kind introduction and for your kind invitation. I'm delighted to contribute to these seminars organized by TATA Steel on hydrogen material interactions. Good afternoon to everyone. As you heard, my name is Emilio Martinez-Paneda. I'm an associate professor at the University of Oxford. And today I want to talk about some of the work that we have been doing on trying to establish sort of a virtual hydrogen lab. So by this, I mean trying to develop a computational platform that would allow us to predict when hydrogen-assisted failures will happen. And this idea of this vision of trying to achieve, I would say, a virtual testing environment for hydrogen-containing environments has been kind of a long-term ambition of mine. I've always tried to achieve this ambition for quite a long time. I mean, the benefits are obvious. We know that virtual testing has saved billions to the automotive and aeronautical industries. So I'm very excited and very keen to bring that success also to hydrogen-containing environments. But this is, of course, not easy, so we've been excellent. So we've been working on this area for quite a while now, and I think that we're getting there. I think that we have now a computational platform that allows us to predict this hydrogen, that is able to deliver predictions of hydrogen-assisted fractures as a function of environment, the material, and the loading conditions. But I'm an optimist by nature, so let me tell you what our models can do. And then at the end of the talk, you will let me know if you agree with me or not. So the motivation for the work is clear. So there's significant interest in using hydrogen for decarbonizing many applications and sectors. But we know that, storing and transporting hydrogen can be a challenge. We know for a long time that hydrogen very significantly degrades metallic materials, and this has a significant impact on structural integrity. You can see some examples here on how hydrogen degrades the ductility of metals, their fracture toughness, and enhances the fatigue crack growth rates. You can see here, for example, how these are uniaxial stress strain curves, and you can see that by exposing metals to hydrogen gas, we get a very significant reduction in the failure strain. You can see here, this is for a pressure vessel steel. You can see that the fracture toughness of this material degrades by orders of magnitude, at least an order of magnitude, from more than 200 megapascals square meter to below 20 megapascals square meter, just by including 6 parts per million of hydrogen. And here, these are Sandia experiments on pipeline steels, and you can see that just 21 megapascals of hydrogen gas are sufficient to increase by orders of magnitude. This is in log scale, the fatigue crack growth rates, the speed at which cracks grow in under cyclic loading. So the problem is very significant, and as you can imagine, having a model capable of predicting this would be very powerful. It would be very powerful because it would allow us to, map safe regimes of operation, and this will very significantly accelerate the energy transition. But it will also be very powerful because it would allow us to answer some of the key questions that are being discussed nowadays in the hydrogen and virtual community. So one of the key questions, for example, is related to the transport of hydrogen through natural gas pipelines. So a lot of people are wondering whether we can use the existing natural gas pipeline infrastructure to transport hydrogen, and under which conditions, what blends of hydrogen, what pressures. One could use models to tackle this, and I'll show you later as well. Also dealing with this, trying to obtain data for this kind of experiments is challenging. Working with hydrogen gas at high pressures brings a lot of health and safety hazards. So other two key questions in the community is whether we can do these experiments in a cheap and efficient way. For example, in our computers, that will be the most cheap and efficient way that we can do those experiments. And we will again show how we can use the model for this. And another key question is, for example, how you correlate decades of electrochemical-based hydrogen research to gaseous environments. So we have been working on hydrogen and bitumen for quite a while now, but we have typically conducted our experiments introducing hydrogen to our samples using aqueous electrochemical solutions. So now we need to find an equivalence between that and the gaseous conditions that are more relevant to the energy transition. And for that, some theoretical and computational efforts are needed. So again, this is another area where models can make a big difference. So let me tell you a little bit of what we can do, and this will be the content of my talk. So I will first start by telling you a little bit of the ingredients of the model. What does the model do? What is the model based on? And then I will show you some representative results showing how the model can predict hydrogen-assisted failures, not only at the lab scale, but also at scales relevant to engineering practice. And then I will finish with 2 case studies that I think will be of interest to many of us here. The first one is trying to use the model to efficiently and cheaply conduct virtual fatigue experiments. So there's only a few labs in the world that are able to run hydrogen-assisted fatigue crack growth tests in the presence of high hydrogen pressures. And we can show with that, the plan is to show with the models first whether we can predict those experiments, and second, whether we can do virtual experiments to fill the gaps, so to say. And then the second one is that, this, as I said before, there's a lot of discussion on whether we can transport hydrogen in existing pipeline infrastructure. And there again, of course, the critical problems related to wells, which are typically the weakest link within that pipeline infrastructure. So we will use the model to show whether we can deliver predictions on what's the critical pressures that we can transport hydrogen in those pipelines. And again, this is another area where models are critical, because we know that, you know, the conditions relevant to wells are very difficult to replicate in laboratory experiments. And it's also very difficult to run experiments on real large-scale pipes, because we know that there's an oxide layer that takes significant time or significant action to be disrupted, and that oxide layer prevents hydrogen uptake. So you may be running these very expensive large-scale trials and getting nothing out of them, basically. So models, again, can play a difference. So let me describe our modeling framework. I think there's two things that I would say here. I guess the first thing that I can say is that there have always been models, in the sense that you can always go to your lab, obtain a few data points, feed those data points with a polynomial function, and then claim that this is a model, but this is, you know, purely fitting. What we wanted to do was to propose a physically based model, a mechanistic model. And by this, I mean a model that explicitly resolves all the physical processes involved in hydrogen embrittlement, and that it takes as input only physical parameters, material properties that we can independently measure in our lab. So this has always been our objective. Only I think by being mechanistic, by resolving the physical processes, by taking as input physical parameters, we can be confident that our model is not only able to interpolate between the experimental data points, but it's also able to extrapolate. And this is key in this hydrogen energy applications. So let me walk you through each of the steps involved in the development of our modeling framework. And I will be dividing the work in the three key stages involved in hydrogen embrittlement. One is the uptake of hydrogen into the metal. This is quantifying how much, for a given environment, how much hydrogen enters the metal. The second one is the transport of hydrogen to the metal, so quantifying the diffusion of hydrogen within the crystal structure and its trapping, sequestration of microstructural defects. And then the last one is the embrittlement process itself, the nucleation and growth of cracks due to the accumulation of hydrogen in critical interfaces. So let me start with the hydrogen uptake. As I said before, the goal here is to quantitatively relate a given environment. It could be a gaseous environment or an aqueous electrolyte environment with a hydrogen content at the surface of the metal, or a hydrogen absorption. And I think the good news here is that when we are dealing with gaseous environments, this is relatively well understood, particularly if we're talking about, you know, steady state conditions. Kinetic effects are another business. But if we're talking about the steady state conditions, then we know that in gaseous environments we can relate, we can use a closed form expression or a Siebert's law or the Abel-Nobel equation to obtain an estimate of the hydrogen concentration at the surface of the metal as a function of the hydrogen pressure or fugacity. And the only thing that I want to emphasize here is that the coupling with mechanics is quite important. As you can see here, the solubility of the material depends on the hydrostatic stress. So it's important not to neglect this term, otherwise you're going to significantly underpredict what is the hydrogen uptake ahead of cracks and other stress concentrators. So that's the good news. The bad news is when you're looking at aqueous electrolytes, when you're looking at hydrogen uptake from aqueous electrolytes, such as seawater, for example, then the picture is much more complicated, because then you need to resolve not only the surface reactions taking place at the electrolyte metal surface, but also the electrochemical behavior of the electrolyte, which can be very different inside of occluded crack environments, such as cracks and pits and other defects, relative to the bulk, which is where you typically conduct your measurements. However, I think the good news is that, well, we know what are the differential equations that describe the physics of the electrochemistry of electrolytes, and we know what are the equations that describe the hydrogen evolution reactions, the Tafel-Borman-Hurwitz and absorption reactions. So we can formulate a theory and then implement that theory into a finite element context and obtain predictions for this. So in this case, as I said, what you need to solve is the electrochemistry of electrolytes. So that means the Nernst-Planck equation and the neutrality condition, and this is for every ionic species that is relevant to your system. And then you need to solve for the Borman-Hurwitz, Tafel, and absorption reactions near the surface. So this is how the finite element model looks like. You may have an electrolyte domain, which has as many ionic species as needed. And then you have an electric potential as well. Then you have a metal domain, which might contain a crack or the type of defect where you're solving your mechanical problem. And then you're also solving for the uptake of hydrogen and the transport of hydrogen. And then you have an interface between the two where you're solving for the hydrogen surface coverage. So I think that the one thing that one immediately realizes here is that there's a lot of degrees of freedom here. So all of these things that I'm saying are degrees of freedom in your finite element model. So you have maybe 12, 15 degrees of freedom, depending on your problem, if it's 2D, 3D, how many ionic species you have. And solving this, 10 years ago was unthinkable, but nowadays computers are powerful enough so that we can solve these problems without issues. And we're also working on developing new stabilization schemes, such as lamp integration schemes that have accelerated these calculations. And then this is the kind of representative result that you'll get. So here I'm plotting on the electrolyte the variation on pH. You can see that it actually changes quite dramatically from the bulk pH to the inside of the crack. And this is you see the uptake of hydrogen inside of the metal. And this is, of course, obtained for a given time. This is after 10 minutes of exposure to hydrogen-containing environment, for a given applied potential, for a given fluid velocity, for a given material. But again, with these virtual platforms, we can change any conditions that we want, and we're able to quantify what is the hydrogen uptake for a given environment. And you can see here predictions of crack tip estimates of hydrogen uptake as a function of applied potential. So here I'm changing applied potential, and you can see that it effectively shows the trend that we expect from our embrittlement predictions. We know that metals embrittle at very low applied potentials, and there's also like a dwell in an intermediate region, and then we have an increase again on embrittlement susceptibility. So everything looks good, and not only you can do this, but you can also gain fundamental insight into what's happening, so you can compare what is the competition between the different reaction rates that are happening into your material. But I think one other aspect that I would say is arguably even more important is that we can finally correlate gaseous environments with electrochemical environments, because we have a tool that allows us to predict what is the hydrogen concentration ahead of a crack for a given electrochemical environment. And then we just need to go back to Siebert's law and say, okay, since we know what is the hydrogen concentration, we can solve for the pressure, and we know that for this electrochemical environment, this is equivalent to testing hydrogen, testing metals in this other hydrogen gas pressure environment. And this is very good because not only allows us to leverage decades of electrochemical environmental research, but we can also do our experiments in much safer and cheaper conditions and obtain meaningful results. Plot our data as a function of hydrogen concentration, which can be directly connected to pressure. So that is one of the key questions, I think, in our community, this idea of the equivalent fugacity that could be addressed with these models. Once we know how much hydrogen we have into the metal, we go to the second stage. We need to be able to predict what is the hydrogen distribution within our component or our microstructure. So quantify hydrogen transport and trapping. And we know that, first of all, hydrogen transport is driven by gradients of hydrostatic stress and of concentration. So it's an extended version of Fick's law. And this coupling with mechanics is quite important. You can see here at the steady state, this is the hydrogen distribution within your material, within your component. And you can see that you have an exponential term that depends on the hydrostatic stress. So ahead of cracks and other stress concentrators, this term is going to be quite significant. So the coupling with mechanics is quite important. But anyway, this is the transport of hydrogen. So by solving this equation, you can predict the distribution of hydrogen within your component. But this is only one part of the picture. We know that hydrogen not only diffuses freely through the crystal lattice, it's also sequestered at microstructural features such as traps or defects. So we have developed more generalized extended formulations that can account for these multiple trapping conditions based on either Oriani's equilibrium or McNabb-Foster kinetics. And I mean, one aspect that I really want to emphasize here is the fact that if you really want to predict what is your hydrogen distribution within your microstructure and you want to consider multiple types of cracks, first you need these multi-trap models because you need to be able to quantify what is the binding energy and the trap density for each of these defects. So you can have hydrogen trap in grain boundaries and carbides, these locations. But also when you're dealing with these locations, you need to take into account the role that geometrically necessary these locations play on this. So we know that typically most of the models that I've seen when it comes to hydrogen trapping in these locations, they consider only the statistically stored dislocations that are related to plastic strains, but we should also consider GNDs, geometrically necessary dislocations, because we know from experiments that they are very significant and dominate dislocation behavior near cracks and inclusions. And therefore, if you want to quantify what is your hydrogen distribution at these locations, you need to be able to quantify these GNDs that are related to plastic strain gradients. And this is only not important not only due to the role that these locations play on trapping, but it's also important due to the role that GNDs play on elevating crack tip stresses. We know that these GNDs act as obstacles to the transport of all these locations, to the movement of all these locations, and therefore bring some local hardening in areas where you have high gradients of plastic deformation. And you can see this here. You can see these are the tensile stresses ahead of a crack tip. So you have a crack here, and I'm plotting the tensile stress ahead of a crack. And you can see that far away from the crack tip, your predictions using these constitutive models that account for the GNDs, so-called strain gradient plasticity models, coincide with conventional plasticity. But as you approach the crack tip, there's a very significant stress elevation associated with the GNDs with these plastic strain gradients. So this significant stress elevation near the crack tip over the critical distance that matter for hydrogen-assisted fracture is going to drive the hydrogen content near the crack tip as well. You can see it here. This is a log-log plot that you're getting predicting much more higher hydrogen concentrations when you account for the role that this GND plays on crack tip stresses. And this is quite important because first of all, we see that only by accounting for the GND effect, we're able to reproduce what we see in the experiment. So these are measures of hydrogen concentration ahead of a crack. And you can see that only by accounting for the GND fees, the solid lines, we're able to capture two trends that we see in the experiment. That the hydrogen content increases with applied load, and that the hydrogen content significantly increases near the crack tip. And there's a lot of experimental evidence showing very high hydrogen concentrations near crack tips. And again, only through these GND effects, you can argue this. And as I show later, this is also important because I would say that this is the only way to rationalize the cohesion mechanisms. We know that the cohesion arguments need higher hydrogen concentration than the higher crack tip stresses, and these GND effects, in my opinion, provide a solid argument behind them. So once you know how much hydrogen you have within your material, within your microstructure, then it's time to predict the fracture, the embrittlement process itself. And one aspect that I would like to mention here is that here the complexity comes from the computational side. Prediction the evolution of cracks or other discontinuities is quite a challenging problem. You may have to apply, moving boundary conditions. You need to change your finite element mesh. It's quite a complicated problem. But there has been a development in the computational fracture mechanics community that, in my opinion, has really changed dramatically the way that we can tackle these problems, has made our life significantly easier. And that is the development of these so-called phase field models. So this is the approach that we followed. And the idea is quite simple. Whenever you have two phases, it could be a cracked phase and solid phase, intact material points. You can treat that interface as discontinuous, or you can smear that interface over a finite domain and use an auxiliary variable, the phase field, to describe where the interface lies. And this implicit treatment of interfaces is computationally very compelling for multiple reasons. One is that the interface equation is defined in the entire domain, so there's no need for any special treatment. The other one is that topological changes such as divisions of merging of interfaces are naturally captured. And a final one that is very convenient here is that the interface equation can be easily combined with equations describing other physical phenomena. And I mean, phase field modeling has been a revolution in many areas of science and engineering. It all started in the condensed matter physics community, where it's now by far the most widely used technique to simulate microstructural evolution. It has very quickly become the dominant tool also in fracture mechanics. And we have recently shown that this paradigm can also be extended to corrosion. So you can use these phase field models to describe the evolution of the corrosion front, the interface between the aqueous electrolyte and the metal, and therefore resolve the physical processes involved in corrosion. But what I'm focusing today is in fracture mechanics, and as you can see, I mean, you can clearly see what is how you can capture problems of arbitrary complexity. I mean, you can see here multiple cracks, crack branching, coalescence of multiple cracks, initiation of cracks on secondary sites. So no matter what the complexity of the problem is, you can see that the method is quite robust. And one key aspect to emphasize here is that these are not only fancy colors, the predictions provided by these phase field fracture methods are physically very sound. And the reason being is that phase field provides a computational platform for Griffith's energy method. So all goes back to Griffith and the foundations of fracture mechanics and the thermodynamics of fracture. As you know, Griffith postulated that a crack will grow whenever the energy stored in the solid was sufficient to overcome a critical quantity, the energy required to create tuning surfaces, which is the fracture energy or critical energy of release rate. And you can postulate this Griffith balance in a variational form. And if you're able to minimize this functional, then you're able to predict the evolution of cracks as an exchange between the energy stored in the material and the fracture energy. However, solving or minimizing this functional is quite complicated for computational reasons, since you don't know where your crack surface gamma is. But here's where the phase field comes to a rescue because we can use the phase field as a marker, interpolating between intermaterial points and fully cracked material points, and acting a little bit like a damage variable. You can see here the phase field goes from 0 in intermaterial points to 1 inside of the cracked and fully cracked material points. And it's a non-local damage model in the sense that you can see here there's a gradient and there's a length scale, which means that all predictions are going to be mesh objective, so independent of the final element and mesh used, as long as you can resolve the length scale. And a little like a damage model, it reduces the stiffness of the metal. You can get a good overview by looking at the governing equations here. So you have a balance equation for the standard balance of linear momentum, where you will have the phase field degrading the load carrying capacity of the material. And then you have an equation for the evolution of the phase field, which is essentially a competition between the energy stored in the material, the strain energy density, and the fracture energy, the energy required to create shear surfaces, a material property that you can measure. And just by solving this additional differential equation, we're able to predict fracture problems of arbitrary complexity. You can see here in this image how you have crack branching due to the application of a dynamic load. And we can predict this complicated fracture phenomena without any convergence problems. The method is computationally very robust and the original final element mesh. And I mean, this slide summarizes why it has been so popular in the computational fracture mechanics community. You can see here that it not only is able to capture very complex cracking phenomena, but is able to do so providing a remarkable agreement with experiments. And so my goal was basically to extend this to hydrogen embrittlement, to extend this access of phase field to hydrogen embrittlement. And I think this was very important to me. When I realized at the time that this was very important, it was going to be very impactful, because phase field in a way not only is computationally very powerful, and this means that it can be used to solve very complicated problems in our labs, but it can also be used to solve problems at the engineering scales. You know, engineering practice often involves very complicated problems, much more complicated geometries and components than where we typically deal with our standard laboratory experiments. And I realized that phase field could give us those capabilities, but also the fact that phase field is so closely connected to fracture mechanics that provides predictions in agreement with conventional fracture mechanics theory was a key factor of it, I thought, because the fact that you are able to, on the very simplistic scenarios where conventional analytical fracture mechanics can give you a solution, provide the same results, means that your predictions are not only going to be built on decades of fracture mechanics research or on a well-established theory, but also your predictions are going to be in agreement with what engineers and practitioners are doing. So in a way, designers are using fracture mechanics in their codes. By using phase field, they're going to be able to predict exactly the same in the idealized circumstances where they are working on, when they need to do simplifications. You assume that you have one crack, mode 1, and so forth, but also allow them to go beyond that and take their fracture mechanics understanding to more complicated scenarios, which often appear in engineering practice. So my goal was to extend this access to hydrogen embrittlement. And if you want to do so, I guess the simplest problem you can solve is a 3-field problem, where you're solving for the deformation of material, the hydrogen transport, and the damage process. And I highlighted some of the couplings here. You can see them in blue. But I think, of course, the key coupling here is how hydrogen affects the damage process. And how this is done from a qualitative point of view is quite clear. We all know that, we have seen in the experiments, hydrogen reduces the fracture toughness, fracture energy of metals. But how to do this quantitatively is the key question. And I think that the good news is that this framework is universal. So there's many ways that you can approach it. One way is, of course, a phenomenological way. And many of our industrial partners follow this approach. We have lots of experimental data of fracture toughness versus hydrogen gas pressure. So we could just feed that data and input this into the model. For example, you can see here, this is for an X42 steel, and this is for other 2 pipeline steels. This is X80 and X52. You can see there's enough data. And this is often good enough because many of the materials that we're interested in, we have characterized them properly, and we understand them very well, and we have data of fracture toughness versus hydrogen content. So there's no need for us to go beyond that. But we can go beyond it. For example, if we're thinking of designing metals with resistance to hydrogen embrittlement, we need to go beyond that. We need to be fully mechanistic. And the good news is that this framework can accommodate any mechanistic interpretation. So you can define your hydrogen degradation function as a function of any micromechanical or macromechanical parameter that you believe is of interest. The hydrogen trapping in grain boundaries, the dislocations, the plastic strain, dislocation density, whatever you believe matters. So let me tell you a little bit of what I think matters. Because, of course, my goal at the very beginning, as I said, was not to provide a model that required a lot of fitting with experiments, but to provide a model that could provide blind predictions that without no fitting or minimal fitting, only measurements of material properties was able to deliver reliable predictions. So for that, we need to be able to define how this degradation, what is the shape that this mechanistic degradation function should take. And this requires answering the question of how does hydrogen make metals brittle? How can it possibly be that a material like this one that fails in a very ductile fashion through microvoid cracking mechanisms in the absence of hydrogen suddenly fails in a very brittle fashion with cracks often propagating along grain boundaries in the presence of hydrogen? And in my opinion, to understand why this happens, how we can just by adding hydrogen into the material, we see this ductile to brittle shift, we need to understand three key ingredients. The first one is that if we look at our problem across the scales, so if we do atomistic calculations, we see a very significant reduction of the bonding strength of metal atoms with hydrogen occupancy. So here you can see DFT calculations for nickel, and you can see predictions of fracture energy versus hydrogen occupancy. And you can see that this is for two types of grain boundaries in nickel. You can see that if your grain boundary is full of hydrogen, if your occupancy is close to 1, then you get a 40% reduction in fracture energy or bonding strength of grain boundary strength. So that's a significant one. But of course, the key question here is, okay, where are we in this x-axis, right? Because if somehow the hydrogen occupancy in grain boundary is over here, then, well, this is a secondary effect, and there must be other mechanisms playing a role. And the answer to that comes from the thermodynamics of trapping. And we can do experiments in our lab. We can measure binding energies. We can see how energetically favorable it is for the hydrogen to go to certain microstructural defects. And we can use Oriani's equilibrium to relate those binding energies with the hydrogen concentration and the trap occupancy. This is what you're seeing here. So this is hydrogen concentration, binding energy, and trap occupancy. And we know, and we can measure in our lab, the binding energy for grain boundaries. And we know that this is higher or smaller than -40. So we are somewhere here. And we can see very easily that the occupancy of my grain boundaries are effectively going to be full of hydrogen for hydrogen concentrations as little as 0.2 ppm or something along those lines. So for very low hydrogen contents, we're already seeing that it is very energetically favorable for my grain boundaries to be full of hydrogen. So if I go back to atomistic calculation, I know that I'm going to be somewhere here, and therefore we're going to have a very significant reduction of fracture energy. So then the question that is missing is, okay, is this 20 to 30 to 40% reduction in bonding strength sufficient to trigger a change from cleavage fracture, from ductile fracture to cleavage fracture? And we know that the theoretical lattice strength of the grain boundary is 9 to 10 times the yield stress. So 30 to 40% reduction maybe is not enough. But when you account for those GNDs, for those plastic strain gradients that I mentioned before, you have these macroscale stresses that are sufficiently high. They're not high enough in the absence of hydrogen to reach the cleavage strength. But the moment you bring hydrogen into the picture, you get this 30 to 40% reduction in cleavage strength, and then these two lines cross, and you have a story. You have a model that is naturally capable of predicting the change from ductile fracture scenarios to brittle fracture scenarios just by introducing hydrogen to the model without no fitting parameters whatsoever, just an atomistic calculation that you need to run once in your lifetime offline. Okay, so this is very easy to incorporate in the model, as you can imagine, because we are solving a multi-physics model, so we are solving for the hydrogen distribution within our sample. We can then use, Oriani's trapping equilibrium to relate the hydrogen concentration to the trap occupancy in whatever interface we feel is relevant, like a grain boundary. And then we just need to go to this atomistic calculation and come here with our coverage and decide quantitatively how much we reduce your fracture energy. So everything can be naturally incorporated into the model. So let me show you some results to show how the model is able to predict our experiments. First, I'm going to show some results on R curves. So these are crack growth resistant curves. So what I'm measuring here is a measure of the crack tip load. And this is the crack extension. And you can see in agreement with experimental observations, if you increase your hydrogen content, then you get a lower fracture resistance, as you see here. Here I'm showing another classic effect or another classic experimental observation, which is the influence of the loading rate. We know that if we load our samples very fast, there's not enough time for the hydrogen to distribute within our sample, and therefore we get less embrittlement. But if we load very slowly, if our loading rates are slow, then we have more hydrogen distribution within the sample, and this brings a reduction in the crack growth resistant curves, as you can see here. But we can also be quantitative. These were qualitative observations. Here's a comparison with experiments on pre-charged steel bars. These are high-strength steels. And you can see that the measurements of notch tensile strength versus hydrogen content are in very good agreement with the model. This is a set of interesting experiments conducted at SINTEF. So here they have duplex stainless steels that were immersed in a seawater bath. They contain a notch, and they were subjected to a constant remote stress. And then the time to failure was measured. And you can see here that these are the dots, or the symbols are the experimental points, data points, and you can see that all of the samples fail relatively early for engineering standards. But we can take our model and not only reproduce the experiments, gaining confidence in our predictions, but also run virtual experiments over very large timescales, which allows us to determine what is this remote stress threshold below which embrittlement will not happen. So this is another ability of the model. We can run very large experiments, either large in time scale or space scales. This is another interesting set of experiments. This is in collaboration with our colleagues at UVA. They were very interested in assessing the suitability of slow strain rate tests, SSRTs, to characterize the susceptibility to hydrogen damage. And their suspicion was that this test was not suitable because cracks will initiate earlier in the test. So we took our model. First, we showed that the model was able to capture the failure time in the absence of hydrogen. We then introduced hydrogen for multiple environments, and we were able to show that the model was actually able to capture the failure times for multiple environments and multiple types of model K500 alloy, which is the alloy that we're interested in here. And what we saw with our model is the model was also able to capture what you see in the experiment. So you get this kind of ductile instability when you're looking at the case in error, the experiments in error. But we saw that the model was predicting that cracking initiated relatively early in the experiment, and therefore made this SSRT experiments not suitable for assessing hydrogen bitumen susceptibility. One has to do fracture experiments. And we can simulate anything. We can simulate many other standardized tests, no matter how complex they are. So we know there's a lot of hydrogen bitumen problems in strength, in anchors and in bolts and screws. So you can simulate this kind of classic STM standard test where you have a screw, metallic screw in concrete, and you have the screw subjected to an aggressive environment, a hydrogen-containing environment. You can see that we can simulate the complete failure of the screw, and we can model anything that we want. So we can model, large-scale components. We can simulate the failure of large-scale components such as pipelines or any other geometry. So effectively, we're bringing this idea of virtual testing to hydrogen-containing environments, and this was kind of our goal. And more excitingly, we can correlate this with inspections. So here you see a pipeline. It's a 12-kilometer pipeline that was characterized by Nicola Rosa and co-workers at BP. And this pipeline contains multiple defects. This what you see here are hundreds of corrosion defects. These are pit corrosion defects. So we can model that pipeline. We chose to model a critical section of 3 meters that contain more of 100 of those defects. We can very easily incorporate those defects into our model because we are solving for the phase field as a degree of freedom. So this is basically an initial condition. And then we can subject the pipeline to in-service conditions, and we can see how those defects start growing. You can see here how they start growing, how they merge with each other, and then eventually how they grow and extend, and you get a complete collapse and failing of the pipeline. You can see it here as well. But I mean, the key takeaway here is that we finally have a tool that allows us to predict when hydrogen-assisted failures will happen as a function of environment, the material, and the loading conditions. And as you can see here, this tool is not only able to deliver predictions at the lab scale, but it's also able to do so at the scales and complexity conditions relevant to engineering practice. No matter what complex the problem is, we can handle it. And it looks a little bit like a video game, but in reality, it's quite a sophisticated mechanistic computational framework that is resolving explicitly all the physical processes involved in hydrogen bitumen. It takes only as inputs physical parameters that we can measure independently. We have also extended this to microstructures. So typically, traditionally, I would say in the hydrogen bitumen community, we were not too worried about the microstructure because we always deal with situations where you have pre-existing defects that are larger than the relevant microstructural length scales. But there's many other scenarios these days, for example, the initiation of fatigue crack in austenitic stainless steels, where microstructure plays a role. And this is also, of course, relevant if you want to design new alloys and you want to test these new alloy designs. But we can extend these models to capture the role of the microstructure, and you can see some examples here where we're simulating in 2D and 3D the propagation of cracks while resolving the anisotropic nature of the microstructure. We have also combined this with those phase field corrosion models that I was talking to you about before. And this is quite powerful because it allows us to develop a generalized stress corrosion cracking models And these are models where we don't have to make any a priori decisions on which is the mechanism dominating the cracking process. We don't need to say a priori, okay, it's going to be hydrogen embrittlement, it's going to be anodic dissolution. We just run our model, we provide environmental conditions, and let the model pick which mechanism is going to be dominant. And that allows us to deliver predictions over a wide range of applied potentials. So for any choice of environment, you can see here that we go from the cathodic regime where hydrogen embrittlement dominates to the anodic regime where anodic dissolution dominates. And we can also capture the interplay between the two. This is, for example, a representation of the classic experiments by Gruhl on aluminum alloys where he was trying to understand the interplay between hydrogen embrittlement and anodic dissolution. Quite excitingly, we have extended this to fatigue. So in addition to having a hydrogen degradation function, you have a fatigue degradation function, a degraded factor energy based on the number of cycles. You can see here virtual SN curves predicted with our model, showing a relatively good agreement with experiments. And these are, by the way, cycle by cycle calculations. So this is computationally time consuming, but we have developed algorithms and methods to accelerate these calculations, and we can do now millions of cycles. But also very compelling because we are able to simulate or deliver predictions for any arbitrary choice of loading history, and also for any arbitrary choice of geometry. You can see here that we can obtain as an output of the model the Paris law behavior for different hydrogen-containing environments, and we can obtain virtual SN curves for, again, any arbitrary loading history, any arbitrary geometry. This is a notch component, for example, and again, hydrogen contents. So let me finish with these two case studies that I think will be of interest to many of you there. The first one deals with hydrogen-assisted fatigue. So we know, cyclic loading is the most relevant loading scenario for many of the applications where we're interested in working with hydrogen in the energy transition. For example, pressure vessels or even pipelines, cyclic loading is relevant. So we need to be able to understand how metals behave when you have a combination of cyclic loading and hydrogen uptake. And this is problematic because, running these experiments is costly, first of all, but also is challenged from a health and safety point of view. However, luckily, there's a few labs in the world who are able to do that. Sandia is one of them, and they're producing data that are very relevant. I mean, they're critical because it's data that is being used by engineers these days to design, for example, pressure vessels for the hydrogen economy. And you can see some of this data here. They have been lucky enough, or they have enough resources to run experiments for multiple pressures, for different loading ratios, different frequencies, and so on and so forth. This is the resulting air, and this is for different hydrogen-containing environments. But we want to go beyond this data. So there's a motivation to try to develop models that are able to produce these experiments, to run virtual hydrogen-assisted fatigue crack growth experiments for multiple reasons. One is that there's a sensitivity to the loading frequency. Normally in fatigue, as you know, we don't care about the loading frequency, but the moment we have hydrogen, we have diffusion, and therefore timescales matter, and there's a sensitivity to the loading frequency. And we know that the lower the loading frequency, the higher the susceptibility to hydrogen embrittlement. So we want to actually test at very, very low loading frequencies. And in fact, we know that in real applications involve very low loading frequencies, for example, pressure vessels for hydrogen charging. But the experiments need to be conducted at relatively high frequencies because otherwise it's very time consuming. And there's also some challenges related to leaks and so on, what you get when you get high frequencies. So it's a problem because we are in the non-conservative side of things. We are doing, fast experiments, and we know that the slow experiments will show more susceptibility, and we know that applications involve slow loading frequencies. Of course, the data is tied to the test conditions. These are experiments that are expensive, and these data points are related to, a specific loading frequency, a specific load ratio, a specific material, a specific pressure. So every time that you want to go somewhere else, you need to work in other regime. You need to come up with more experiments. Every time you want to test a new material, you need to do more expensive, and all of these tests are, as I said, quite expensive. Also, we want to obtain life estimates for arbitrary loading histories, but these tests are conducted at constant load amplitudes, and we're also disregarding the crack initiation stage, so we want to be able to incorporate them into our model. So we said, okay, the good thing is that we have data to test our model. Let's see how our model behaves. So the first thing is that we try to calibrate our experiment with the response, our model with the response in air. So this is, again, as I said, fatigue crack growth curves versus applied frequency. This is the Paris law behavior. This is for a given load ratio and frequency. So we run our experiments. We basically subject our compact tension samples to cyclic loading conditions. As you can see there, we propagate a crack, and we measure the speed at which that crack is propagating. And we know the fracture toughness of the material, so we just need to calibrate the fatigue degradation function, and then we're able to show that, by calibrating this fatigue degradation function, we're able to capture how this material behaves in the absence of hydrogen. Now there is data for hydrogen for multiple pressures. This is, for example, they have data for 55 megapascals. So we said, okay, now let's not touch anything in our model. And let me emphasize this. I'm not touching any parameter of my model. My model remains exactly the same. The only thing that I'm doing to my model is that I'm enabling hydrogen diffusion. I know what is the hydrogen concentration that corresponds to this pressure of 55 megapascals. I'm putting that as my boundary condition. I'm pre-charging a little bit my sample, 24 hours, as they do in the experiments, and then running my test. The only interplay between hydrogen and the fracture resistance of this material is that fracture energy reduction with hydrogen content that I showed you before, that is well characterized for this pressure vessel steel. So we do have a proper fracture toughness versus hydrogen content curve. So I'm going to run my virtual experiment with fatigue, and this is the response that I get. So again, the symbols are the experiment, the solid lines are the computational predictions. So a very good agreement. And then they also have data for 106 megapascals, so higher hydrogen pressure. So again, I change the pressure on the hydrogen content in my model. Again, I don't touch any of the parameters of the model. This is a completely blind prediction. Again, a very good agreement. And they have data for different loading ratios as well. You can see here for different loading ratios. And I don't know why this cap in there, but you can see data for different loading ratios. So again, we take our model. We change, again, we don't touch anything in our model. We just change the loading ratio. And again, we get a very good agreement all across the board for loading ratio of 0.1, 0.5, and 0.7. And this is, by the way, for a pressure of 55 megapascals, but they also have data for a pressure of 106 megapascals. And you can see here that, again, we don't touch anything in our model. We just change the loading ratio on the external hydrogen pressure, and we get a very good agreement with experiments. They also have experiments for different loading frequencies. Again, not touching anything in our model. I'm just going to change the loading frequency. And again, a very good agreement with experiments. And this is for a load ratio of 0.5, but they also have data for different frequencies in 0.7. We change the frequency, we change the load ratio, not touching any of the parameters of the model. There's no fitting here whatsoever. Again, a very good agreement. So this gave us confidence that the model is very robust and is working very well. So we were quite excited about this ability of the model to blindly predict the different scenarios, changing loading frequency, pressure, and load ratio. But then we said, okay, let's use the model to try to understand things that we don't not figure out from the experiment, right? That we need to know that we cannot figure out from the experiments. One thing is that these experiments are done as soon as possible, basically. So you don't pre-charge your samples. You have to pre-charge them for 24 hours because that's the time that it takes to get the machine set up and running. But then after that, you just load your sample. So we wonder, okay, maybe this is not the most relevant scenario. It could be if you have an oxide layer, but maybe it's not the most relevant scenario to real applications where you may have your pipeline or pressure vessel exposed for a very long time to hydrogen. So what we do is in our experiments, we pre-charge our samples. And unlike the experiments, in our virtual experiment, we can do this quite fast. That's the reason why they don't do it in practice. So we can pre-charge our samples quickly, and then we run the fatigue experiment. And this is what we see. So we see an increase in 2 to 5 times in the fatigue crack growth rates versus the data obtained in the absence of this pre-charging. And then, I don't know if 2 to 5 times is important or not. That is, for the engineer to decide whether this increase in fatigue crack growth rate is important or not. Another aspect that we can do is the role of frequency. I mentioned before, the experiments are typically conducted at frequencies of 1 hertz because this is what is practically convenient. From time to time, there are experiments being conducted at lower frequencies, but this is very expensive. And also, they're a bit afraid that maybe they'll have some leaks at this very low frequency. It's quite challenging to do experiments at low frequencies. So what we can do with our model is we can do virtual experiments at a wide range of frequencies. And what we can show is actually that we see the expected trend. So we go from 2 plateaus to limiting cases when we load so fast that there's no time for the hydrogen to distribute within the material, and when we load so slow that hydrogen has all the time that it needs to achieve the steady state to uniformly distribute itself within the material. And what we can see is that our predictions are in good agreement with experiments. So that's good news, I think, for both of us. For us, because it shows that our model is robust and continues to be robust in predicting experimental responses. But also for the experimentalists, because it means that maybe those things that they were worried about, like leaks, are not really playing a big role. But the other piece of good news is that we see that in this limiting case, it's again not too far away from those crack growth predictions that you get at 1 hertz for this particular material. So again, it could be that, they're running the experiments. They're not being non-conservative, but they're running experiments in a scenario that is sufficiently close to reality. And let me just finish with this very last case study. This is related to, again, one of the big questions that we have in our community these days. Can we use the existing natural gas pipeline infrastructure to transport hydrogen? And of course, the key problem here is to be able to predict the structural integrity of wells. Will the wells be able to withstand hydrogen, and what pressures of hydrogen will they be able to withstand, and what hydrogen levels, what hydrogen purity can we transport? Ideally, of course, we want to transport pure hydrogen, and we want to do that at very high pressures. And as I said, this is very complicated to determine experimentally because, well, it's very difficult to capture, what are the conditions in the heat affected zone. We cannot produce standard compact tension samples from the heat affected zone. So the wells are too complex to test experimentally, one could argue. The other aspect, and you have also residual stresses, of course, so it's quite a complicated process to test experimentally. And the other aspect of it is that real scale tests are also quite complicated because you have an oxide layer that prevents hydrogen uptake. So you may be running a large scale test that is very expensive and figuring out that, nothing is going to happen. And then in practice, after 10 years, you get disruption of this oxide layer, or due to fatigue, you get disruption of this oxide layer, and suddenly you get a structural integrity problem. So we can use the model for that. And here we have a model that simulates two stages. First, we simulate the welding process. So we are able to predict what is the residual stress distribution. And there's a lot of nice work being done in the welding process community, where we have very sophisticated models for predicting what is the changes in phases and residual stresses during welding. And then we couple that with those models that I showed you before. So we're able to predict the structural integrity, those cracking patterns in the present parts. And first things first, we want to make sure that the model works well, that the model is able to capture, for example, the plastic dissipation, what you get when you get sustained crack growth. So we've simulated the crack growth curves for the two materials that we're interested in here, which is an X80 and X52 pipeline steels. And you can see that we get a very good agreement with experiments both in air and various hydrogen pressures. So with this model that we trust and that seems to predict quite well the fractal resistance of metals, we first conduct those welding process simulations. So we apply a torch. In this case, this is a seam weld. It has two passes, so we can predict what is the distribution of the hydrogen content in there, the temperature, the stresses, and accumulated plastic strains. Then we expose that weld pipeline with those residual stresses to a rising hydrogen pressure. And you can see here on the top how the hydrogen distribution grows as you increase your hydrogen pressure. And then eventually you get this propagation of a crack. And basically what we want to do here is we have two scenarios. One is what we call plastic collapse. So a situation where, you get complete yielding of the pipeline before cracking. This is what we want to have. And the other one is a situation where you have brittle fracture before this plastic collapse scenario happens. And what we do is we increase the pressure until we see this brittle fracture happens, so we can quantify what is this critical pressure at which you can transport hydrogen in existing natural pipelines. Then we use the model to answer questions that we want to understand. The first one, for example, is whether residual stresses matter or not. We found that for the X52, residual stresses did not matter. This is a more ductile material, less susceptible to hydrogen embrittlement. And in both cases, with and without residual stresses, in the absence of defects, we found that cracking was due to, the failure was due to plastic collapse. However, in the X80, which is a more brittle and susceptible material, we found that incorporating residual stresses made a change from this kind of plastic collapse failure mechanism to this brittle cracking failure mechanism. And you can see this is attained at a pressure of 31 megapascals. So residual stresses can matter depending on your material and conditions. We also wonder about whether, the porosity that comes naturally from the welding process will play a role. We found that it plays a little bit of a role, but not significant. So this only played a role in the X80. And as you can see here, when we move within a sensible range of volume fraction of microvoids, we only see a small drop in the critical fracture pressure. We go to 24 megapascals for this, 0.5%. Of course, what we were very worried about was the role that pre-existing defects will play. These are vintage pipelines that have been there for 50, 60 years, so we suspect that there will be defects in there. So we tried to conduct a systematic study where we try different sizes of defects along different orientations. And what we found is that the most critical scenario, as you would expect, is one where you have defects lying along the heat-affected zone. And we saw that these defects of 3 millimeters could reduce the critical pressure to 15 megapascals. And this is important because, first of all, those defects have been reported to exist. We know that these kind of defects along heat effector zone of this size are observed in wells. And second of all, because this is a pressure, a critical pressure that is within the range that, you know, gas distributors are considering to transport hydrogen. And the other aspect is, of course, the role of the microstructure. We know that the microstructure can be very heterogeneous. So in this case, we have, this is a working collaboration with EPRI, I forgot to say, so they have very nice hardness maps. And they can use this hardness, we can use these hardness maps to quantify the microstructure heterogeneity of the microstructure. And then we can, you know, make our properties depending on this heterogeneity. So we can have, for example, these small regions, these thin regions of harder material, which are more susceptible to hydrogen. And when we account for these things, we see a 50% reduction in critical pressure. So microstructure does play a role in this aspect. That's all. That concludes my talk with a few last-minute concluding remarks. The first thing that I will say is that recent developments in the computational mechanics community, namely multiphysics modeling and phasing modeling, have been key to develop very robust and mechanistic tools that allows us to resolve the physical processes of hydrogen embrittlement. So we are able to eliminate assumptions by basically applying brute force, by resolving explicitly each of the processes that are involved in hydrogen embrittlement. And this allows us to be physically based, to be mechanistic. This means that our model is dependent only on parameters that has a physical meaning that we can measure in our lab. And our model can be quite general. So whether you agree on my interpretation of hydrogen embrittlement or not, you can use this to your benefit. And we have seen other groups using this, for example, to incorporate help mechanisms or combination of the cohesion and help mechanisms. And you can incorporate this method very quickly to other phenomena. You can capture the microstructure, welding process simulation, stress corrosion cracking. So it's very universal. It is already, in fact, part of already commercial finite element packages. So it's easy to use, it's quite universal, and it can handle complicated problems. I think one key aspect of it is that it's, you know, it's grounded on the thermodynamics of fracture, it's physically sound, and it's computationally very compelling. So it can capture, as I said, in a physically based manner, not only fracture and fatigue experiments in the lab, but also can handle the very complex conditions and large scales inherent to engineering practice, effectively bringing this virtual testing paradigm to hydrogen-containing environments. And I think there's multiple things that you can do with this model, but two case studies that I wanted to show today was one that we could do virtual fatigue regrowth experiments for arbitrary conditions. These conducting experiments, hydrogen gas fatigue experiments, is expensive and problematic. You can do this very cheaply and very efficiently with this model. We have shown that the model is able to blindly predict the Sandia data and is able to extrapolate and interpolate beyond that data. And also you can handle other conditions that you cannot handle in the lab. For example, we have shown you today that we can determine what are the maximum admissible pressures that you can use to transport hydrogen in the existing natural gas pipeline infrastructure. So just I'll conclude by saying that all the codes that we have developed are openly shared. Many of the commercial finite element companies are also adopting our models. COMSOL, for example, has included some of our hydrogen embrittlement models in there. And we have used a variety of softwares. We use sometimes commercial finite element packages, such as Abacus or COMSOL, but also open source, such as Phoenix or in-house codes in MATLAB or C++. But all of them are available for you to download in our website. And if you have any questions while using them, please feel free to reach out to me. But you should be able to reproduce all the results that I've showed you today easily at home. And of course, I must acknowledge the financial support by my sponsors and EPSRC, ERC, Starting Grant, UKRI, and then also EPRI and so. Thank you. Thank you very much for your attention.